This is miscellaneous exercises in the area of differential calculus part 3. So have a look at this. It's only one example, but I think you'll find it interesting. Let's have a go at it. Find the derivative of y equals the modulus of x minus 1 over the modulus of x plus 3 and sketch the graph of y and dy dx. Now, the first thing to do, guys, is when you see this thing here, see that thing there? Look, the first little trick is very, very easy. You just turn it into that, because they are one and the same thing, okay? The modulus of this over the modulus of this is simply just the modulus of this over this. If you care to have a think about that and examine that with some examples, you'll see it's absolutely rock solid truth, okay? Now that saves us a lot of grief. Now we've just got to simplify this expression in here and basically decode it, okay? So you can firstly divide by the denominator, which you always do in these kind of questions. It's basically what's called an improper fraction, where the degree of the top is not less than the degree of the bottom. So just to simplify what it actually looks like, you long divide the denominator into the numerator, or you can simply do this marvellous little trick that I do when the degree of the numerator and the denominator are degree 1, that is x to the 1. So yes, look at this, see? So I'm saying, okay, I want to make this numerator like the denominator. So x plus 3 is the denominator, so I'll call it x plus 3, then I'll subtract 3 straight away so that I haven't changed the numerator in any way, and we also had the minus 1. But now look what that does. See, we can separate off the fractions now into x plus 3 over x plus 3 minus 4 over x plus 3, alright? And see what we've got now. Look at that. Now, that's a completely different picture in terms of how we can look at that now, graphically, from what you had in the first instance, okay? We can now decode it, in quotes, to basically turn it into a hybrid function, and then it'll be easy for us. Now, if we think about this graph here, we do know what this looks like, okay? We do know what that looks like, and that's just a vertical translation of 1 unit, okay? 1 unit up. So it's going to look like this once you analyse it. There's the asymptotes, and there is the actual graph there, okay? Once you work it out and you work out your x and your y intercepts, that's what it's going to look like, okay? Yes, there's an x minus 3, there's a y plus 1. I think you agree, don't you? Yes? Yeah, okay, good. Now, hence for the modulus of that, okay, because this is only just dealing with that, what's in the modulus sign. Hence, for the modulus of that, remembering that what we do is we reflect the parts that are below the x-axis about the x-axis so that they are above or in the positive. So this part here, guys, there to there to there, as far as x equals 1, has to be flipped and reflected above, so it goes like that, if you want the modulus of that function. Do you see what I mean? Yeah, okay. Well, therefore we can say that y equals that thing, which was what we had in here, right? From minus infinity up to, but not including the asymptote at x equals minus 3, or from 1 including 1 up to positive infinity, but leaving out this negative bit here, right? Okay? Yeah, that's what it is for that part of the domain, and for the other part of the domain it's the negative of that to turn the already negative bit under the x-axis into a positive thing, okay? Going from minus 3 not including to plus 1 not including, because I've dealt with the 1 with a square bracket up there for that part of the function, alright? So that's what our decoded hybrid version of what we're seeing over here and here and here will be. Okay, we'll summarise that now and we'll say it's this. Okay, so y is that beastie from there, and it's the negative of the beastie from minus 3 to 1 non-inclusive, right? Now to do the derivative of this is very straightforward. You just take the derivative of each of these components, but you have to be very careful about this cusp here. You can't have the derivative defined at a cusp, so therefore you would round bracket that bit. So there we have it. Derivative is straightforward. this is something minus something to the negative 1, which will get us plus that something to the negative 2. This doesn't get us anywhere as far as derivatives are concerned, so it's just this. And we've got the same domain except I've round bracketed where that cusp is. Yes? Okay. And this one here, similar to what we just did for the first component, it'll be minus 4 over x plus 3 all squared, where x goes from there to there, same thing as what it was up there. Okay, so that's what it is. Now we need to do the sketch graph now. That'll be very straightforward as well. So we'll do y first of all. There are our two asymptotes, and let's fill in the detail. So yes, this was that bit there was as it was before. This bit here used to go like this, down there, and the part that's under the x-axis has been reflected, so it is above it. Okay, and that's what it looks like. Yes, you happy? Very good. Now dy dx, now we have to deal with that. From the graph of y, you can see, ladies and gentlemen, you can see there's a step change in gradient from negative here to positive there, instantaneously at the cusp where x equals 1. Okay, so let's just have a look at this. If x is equal to 1, if x was equal to 1, and we had dy dx was this component here, alright, let's substitute x is 1 into that, we get plus a quarter. On the other hand, if dy dx was this this component of our hybrid here, okay, we substitute x is 1 into that, we get minus a quarter. So you can see there's a discontinuity here, yeah, from negative a quarter just immediately infinitesimally to the left of where x equals 1 here, where it's minus a quarter, and infinitesimally to the right of where x equals 1, it would be plus a quarter. And of course it's not defined where x equals 1 because you can't take a tangent or a gradient line on a pointy bit. It just doesn't make any sense. The curve has to be smooth to enable you to take the tangent. Okay, so therefore this is my NB saying that dy dx is not defined at x equals 1, so we must represent this graphically with open dots at the point of discontinuity where x equals 1. Okay, so let's go over the screen now and have a look at it. Okay, just recapping where we got to, that's dy dx, the two components of the hybrid of dy dx, and look at that. Let's see what we've got here. This part here, there, and this part over here, this part to the right of where x equals 1, but not including x equals 1, correspond to this part of our dy dx function, and this part down here corresponds to this part here, okay, which was reflected about the x-axis because of the reflection about the x-axis of the corresponding part in the function of y, okay, and therefore the graph of y. Now, just a couple of little things of note here. This is a point of scale which I've put in there so that we can adequately express that there's a 4 up here in the numerator. Okay, I've done a y-intercept here. I worked out the dy dx in this part here. If you make x equals 0, you'll get minus 4 over 9 for dy dx, hence this y-intercept here. And there, this is our point of discontinuity where the graph morphs from dy dx is minus a quarter up to dy dx is plus a quarter, where x equals 1, and of course 1 is not included. It's not defined at the cusp where x equals 1. Alright, now I've got some CAS happening over on the screen just to show you what it looks like in a CAS graph format. I've got both functions plotted on the same axes. So, my goodness, look at this. There's the y one. There's our unfriendly looking modulus thing there, which we basically made short work of, didn't we? So we've got this untouched branch of our original hyperbola, and then we've got this reflected one here, right, because that was originally under the x-axis. That's the bit that's reflected, so it's above, where the x-axis acts as a mirror image, and there's our cusp, and there it goes flying off there like that. That's part of the original hyperbola. This is part of the original hyperbola. This is the reflected bit of the hyperbola, and hence the cusp here. Now, the red graph is dy dx. Okay, I think that just about says it all, doesn't it? So I hope you enjoyed it, and remember that they won't ask you something as complicated as something like this in a tech-free exam, and that it would probably be fairly trivial in a tech-enabled exam, but it's great to do the practice to get confident because it does wonders for your psychology. Yes? Okay, thumbs up for everybody. Thank you for coming to be with me. Have a wonderful day, and we'll see you next time.